Welcome back to link layer module, and in this part I'm going to be talking about Wi-Fi. So first of all, Wi-Fi properties. So in principle, Wi-Fi is quite similar to Ethernet, but as you can see on this slide, it's quite different. So first of all, unlike the connectionless nature of Ethernet, in Wi-Fi, you technically, depending on the mode, you actually have to have great associations. So meaning, if there's an access point, you cannot just start communicating, but rather you have to join that Wi-Fi network. There is still a mode, the so-called ad hoc mode, in which you can kind of have the same way of doing business as in Ethernet, but it still requires some form of a setup, and not all systems actually support this mode. The second difference is the way Wi-Fi operates. So while it's still providing unreliable delivery, so it's kind of don't guarantee that every frame that's being sent out over Wi-Fi will be delivered, it actually provides a level of guarantees that the frame will be delivered. The basic logic here is Wi-Fi is much more unreliable channel, and if we kind of offload everything to higher level, then we potentially have a very bad probability of delivering traffic. And as you already know, TCP is quite sensitive to losses, and if those losses not necessarily congestion related, then something bad gonna happen. So what Wi-Fi is trying to do is simply send a frame and wait for the acknowledgement. And if acknowledgement doesn't come on Ethernet level, not TCP level. So if acknowledgement doesn't come, it will retransmit again. Again, the acknowledgement didn't come, it will try it again and again, up until X times. And this X is really dependent on the configuration. You can think of it 5 times, maybe 7 times. So it will try its best, but it will not effectively guarantee. And finally, another difference is the way we access the medium. And in the simplest case, Wi-Fi is using CSMA-CA. Well, all of you are already familiar with Wi-Fi. You're using Wi-Fi probably every day. You have Wi-Fi network at home. I use it in FIU. Wi-Fi can be actually quite complex. And as we can see on this slide, Wi-Fi network not necessarily can consist of a single access point. So this is potentially kind of access point and stations. So this will be representing the network at your home, and in some homes actually it's already not the case. But if you consider a FIU network, like FIU secure network, then the network itself is actually consisting of multiple access points representing the same FIU network. So this is like the same FIU network, in this case will be ESA, or Extended Service Area, that is represented by BSS, or Basic Service Set, represented by individual access points in this network. One interesting aspect about traditional Wi-Fi networks is that access points actually have to be connected over the wire. So this DS, or distribution system is actually have to be some form of Ethernet. Maybe it can be optic cable, but some form of wired cable, because you cannot really, with a few exceptions, connect them over the wire. And then there's a few more things that, as you can see, there's external service set, independent basic service set. So this is additional modes for different types of operation. There's actually a few more interesting new additions to Wi-Fi standards. So there's one that is quite interesting. It's called Wi-Fi Direct, or there's also a different name, or AirDrop if you're in an Apple environment. So this one is a kind of a weird case of access Wi-Fi. While it's still behaving in the same way as infrastructure mode, it doesn't actually require the access point. So when you're creating like Wi-Fi Direct network, or kind of trying to share files or something over AirDrop, one of the phones, one of the devices will be acting as the access point, and will kind of either transparently or in some programmatic form will provide the information and credentials to the other device. So in principle, you can do this point to point when one device is randomly picked as access point and the other device is acting as slave. But you can also kind of in some cases, in principle again, you can run it as a multi-device environment, where again, one device is acting as single access point, and all communication between this device and other devices, or between other devices, is actually happening through this fake access point. So this is just interesting mode that is currently being active. As I promised last time, I want you to remember the Ethernet frame, or the simplicity of the Ethernet frame and be a little bit excited or get crazy about the Wi-Fi frame. And this is actually not the whole picture of the Wi-Fi frame. It's only the traditional Wi-Fi, like 82.11. But essentially what I want to highlight is a few more addresses. There's a control frame, there's duration, there's a payload, there's CRCs. But what's important for the class specifically is addresses. And what you can see, there's actually 4 addresses in this picture. And this is like at least 2 more than what we saw in Ethernet address. And to highlight what exactly is happening with those addresses is the fact that we're doing transmission over the wire. And not just the transmission over the wire, but some of the transmission are going through the access point. So this is like through the infrastructure mode. And we actually need this information in order to transit those frames through the access point, and they will be delivered to the right place. But one more complication. In the Ethernet, if you remember, we only had the data frames. So we had the data, we send the data, and that's it. And not the same thing in Wi-Fi. In Wi-Fi, at the very least, there is some form of a management frame. There is some form of a control frames. And then we actually have a data frames. So, for example, for management frames. So this is the kind of some of the exchanges that you will see as part of the access point telling others that it's present in this environment. So like, how do you know that right now we have so many Wi-Fi network connected, like available to us? This is what management frames are doing. So they simply access point is sending out to everybody that this is the frame that is currently available. And for the control frames is kind of one examples of those would be acknowledgement. And data frames, this is actual data being sent out somewhere, like by the stations, and to be delivered to the destination. And as you can see, not in all cases, all 4 addresses are being used. And even in data frames, it depending, so there's like multiple options what this address 3 and address 4 representing. And there's always a very definitive definition of what address 1 and address 2 are representing. But I'll try to cover with an example what exactly is happening with the data frame. And imagine the case that station A is trying to send some kind of a frame to station D. In this example, we assume that the A already figured out the MAC address of D, so it knows about it. But in principle, it will do exactly the same as you do in Ethernet. It will run ARP protocol, kind of asking what is the MAC address for the this specific IP address, and some of the nodes will reply. So there will be broadcast in one way and hopefully a little bit less than broadcast in the other way. But in this case, we already know the MAC addresses. So what happens? And what happens is at the first stage, as already highlighted, for the receiver station, like for the address 1, you specify who is intended receiver. And in this case, you actually didn't specify that the receiver is D, because station A is communicating only with access point. It's one of the key aspects of infrastructure mode of the communication. Then for the transmitter address, it's in all cases, absolutely in all cases, it will be your own MAC address. So the station who is transmitting, this will be the MAC address of that station. So in this case, it's simply MAC address of A. So that's very simple. And as you can see in all other cases, for the frame, for the frame on the C, we also see the transmitted address is C. So that kind of the station is transmitting. Okay, so now it's a kind of a complicated case. So for the address 3, we actually have multiple options. So we have a BSSID, we have SA or SDA. So it's either basic service identifier, it is a source address, or it is a destination address. So which one is in this specific case? And what you can think about this is actually based on the fact what information needs to be, what information is basically missing, and what you need to specify. And in this case, the missing information is the destination. So we still we specify that we send in to B, because that's what the transmission is right now. We send it from A, but we didn't say where this frame is supposed to go. And this is exactly the address where we're placing this information. We include in, as part of the address 3, the final destination. And finally, as part of the last case, we need to specify it's either BSSID or source address. And in this case, we don't need any additional information. We simply specify that it's BSSID. And in this case, it's specified B because B is a MAC address of the access point, and is in this specific case is acting as BSSID. So that's we covered the first frame. Now, what happens in case of the Ethernet wire? So this is actually an interesting part. So all that information that was available as part of the Wi-Fi segment now kind of don't actually exist in Ethernet. So in Ethernet, we're still doing the same thing that we did before. We specify the destination, the final destination address, and we specify kind of the original source. So basically, we extract information from the transmitter, or it has to be like somewhere from the source. We extract information from the destination, and we're basically creating this frame. So with destination D, that was destination D, and the source A. So that's with source A. That's it. So this is the frame will be delivered to kind of essentially everybody in the environment, and hopefully there is some form of a switching tables available in Wi-Fi routers as well that will properly kind of direct this frame towards the C. So now finally we get to the point of C is trying to finally transmit the frame to deliver to D. And in this case, again, I already highlighted for the transmission address, it will be C as usual. For the recipient, it will be address of the actual recipient. So in this case, it will be D. And for the address 3, we now need to identify either BSSID, if nothing else needs to be specified, or whether it's a source address or destination address. And in this case, what we're missing actually is source address, because we now have a destination, we have a kind of transmitter, but transmitter is not the source. Source was A. So we need to specify as part of the kind of address 3, we need to specify source address, and this is A. We don't actually need to specify any kind of flags to identify whether it's one thing or another. It basically will follow the logic from these addresses. And as part of the address 4, we simply we don't have anything missing at this point, so we specify BSSID, and that's effectively it. And kind of in this case, BSSID is C, which is the MAC address of C, MAC address of this access point. Okay, so this is a little bit of complex, but just remember, like whenever you send the frame, you have to specify the receiver address, kind of immediate receiver address. You have to specify your transmitter address, like the one that you're transmitting. And if your receiver is not the final destination, then you have to specify the address on the other side. I already hinted that those 4 addresses in a Wi-Fi frame is actually not the limit. And one of the examples of going beyond this limit is mesh Wi-Fi, or Wi-Fi mesh, which is a reasonably new standard 802.11s. What they're trying to fix is to make sure that access points can be connected wirelessly instead of them to be kind of connected over the wire. And in addition to that, they wanted to have all sorts of backwards compatibility, like to work with the traditional Wi-Fi and work with the traditional Ethernet. And as a result, there's a little bit more complication on top of those 4 addresses, as already highlighted. So we've added 2 more. And again, those are not used in all cases. I'm not going to actually go over examples. I just want to kind of highlight 4 addresses is not enough for the Wi-Fi mesh because you need to sometimes identify not just the transmitter, not just receiver, like in immediate segment, but also the original source, original destination, basic service set that you're communicating with, and potentially some form of a proxy where your frame needs to go in order to be actually delivered. And if somebody wants to give me additional description of how exactly Wi-Fi mesh is operating, I will be willing to give additional extra credit for this. Now we're done with the basics of Wi-Fi in general, and I just want to introduce you kind of the concept of Wi-Fi is actually not just a single standard. There is like a lot of standards that are currently available, and it's still evolving. Everything started in far away in 1997 when IEEE defined 802.11 standard. So this standard was operating in 2.4 gigahertz range and also was available as part of the infrared. And it defined to use barely this 1 or 2 megabits per second. It's very slow compared to what we have today, but luckily it's no longer actually in use. So luckily. Then there was a modification of the standard, and in '99 we actually got the definition of kind of 11A and 11B standards. So those are a little bit more familiar to you. 11A actually defined 54 megabit per second to operate in a 5 gigahertz range, and kind of 11B standard defined 11 megabits per second and to operate in 2.4 gigahertz range. And even though this standard was defined basically 20 years ago, it's still alive. There's still a lot of devices that supports exactly 802.11b standard, and there are still new devices, new chips are made to support that specific standard. And one of the reasons is basically legacy mode. It's supported by every imaginable hardware, and the chips, if you want to embed them, I don't know, in some of the devices that don't require too much throughput, is actually quite cheap. And in addition to kind of that standard in '99, we had the G standard that basically extended a little bit kind of standard B to increase the throughput inside the 2.4 gigahertz. So that's basically what we had at the kind of up until a certain number of years. But then we actually have a few more explosions in new standards. So we have 802.11n. So I guess some of you are using this today. There are standards AC that's been already kind of standardized, and there's a lot of equipment based on AC standard. And there's actually a few more developments on top of that. So I think the latest one that people pushing forward is standard X. And the interesting part of whole this numbering scheme is actually again changing, because they're introducing different numbering schemes. So there's a Wi-Fi 5, Wi-Fi 6, and kind of they just switch into different numbers to kind of simplify the picture. But for our discussion for this class, just remember the first one, remember B standard, A standard, G standard, and maybe some kind of newer standards. And what I want you to remember is which frequencies they operate and what bandwidths kind of they provide for you to use. Now, one kind of small conversation about the kind of frequencies, why we're picking different frequencies, or what's actually the point. So there are a few actually reasons to pick that specific frequency range. So we have a 2.4 and around 5 gigahertz in the United States. And one of the reasons we pick them is because you don't have to pay money. So like long time ago, FCC has defined that there's like a certain ranges in frequency bands that can be used for whatever reasons. Like anybody can use those frequencies. If you want to go like broadcasting range or some other special ranges, then you have to actually purchase them, purchase rights to use those frequencies. And I guess you heard in the news that some mobile operators paid quite amount of money to actually purchase the right to use certain frequency. But that's kind of a side point. In addition to kind of the fact that it's free, there's also other considerations. And other considerations are regarding the properties of the Wi-Fi. Kind of depending on the frequency, it's actually have different properties to propagate through objects. I mean, depending on objects, of course. So for example, kind of a 2.4 would have a better chance to propagate through some smaller walls than a 5-something gigahertz range. So that's kind of one of the reasons why you can have a higher throughput, but a little bit less distance from the access point. And in addition to that, depending on how signal propagates, how many interference, how many reflections it actually has, then signal can get lost or kind of attenuated in the wrong way. There's actually a lot of interesting research happening how you can leverage all those multipath propagation, but that's kind of outside the topic of this class. What I want you to remember in this class is a little bit about the bands. So first of all, in 2.4 gigahertz bands, originally they defined 11 so-called channels. So that was defined as part of this original standard, as part of the B standard, but then something changed. So the thing is, each of those channels is simply 5 megahertz bandwidth. If you have an electrical engineering background, it will be easier to understand, but just look at exactly what's happening in the picture. So channel 1 starts somewhere at the 2.4 and covers 5 megahertz of space in this case. Channel 2 starts with 2400 plus 5 and kind of cover another 5 and another 5 and another 5. So those 5 megahertz is sufficient for the original standard and was sufficient for B standard. But when they defined the G standard, they actually cheated. And they cheated in terms of they actually defined it to use 4 of these channels. So it's instead of using 5 megahertz, they start using 4 kind of 20 megahertz channel. And as a result, this magical 11 channels are effectively kind of converted to have only 3 non-intersecting channels. So basically, if you send out traffic on those 3 channels, you're not going to interfere with each other. And if you mess up your configuration and you have like some different configuration, as shown on this slide, then it's actually not good. Because in this case, somebody configured to use channel 5, which basically interferes with the kind of channels from 1 to 4 and channels from 5 to 8. So it's kind of really, really bad configuration on the part of FIU SCS research in this specific case. But again, so remember in 2.4 gigahertz, in principle, for United States, we have 12 channels, but we only have actually 3 non-intersecting bands that can be used for the purpose of G standard, AC, and all of them also using this 20 gigahertz combined channels. Luckily, picture is a little bit different for 5 gigahertz. So when they define the 5 gigahertz band, they actually define them in reasonably better throughput. So in these cases, we don't actually have the problem of overlapping. So if you're using specific 5 gigahertz channel, then that's yours. If you pick another one, you're not going to overlap accidentally with some other channels. And these are 12 channels that I showed you on the slide to represent what being used in the United States. And this is another picture that I actually captured a couple of days ago, just to highlight that things are actually getting improved from the perspective of configuration. So basically inside the environment that I was capturing, people are not using kind of wrong channels. In this case, we have somebody configured for the first set of channels, so for the channel 1, somebody configured for the channel 6, and somebody configured for channel 11. So and in this case, nobody is actually intersecting, nobody interfering with each other. So this picture is much better than this picture that I showed you on this slide. And for the 5 gigahertz range is kind of, you can see what's happening. And so I would just recommend you, if you on macOS, just download this Wi-Fi Explorer Lite and just run it. Run in your environment, and you'll kind of figure out how many different networks available around you. And not just networks, note here is not just networks, but rather individual access points. So as you can see on the slide, there's a multiple EG-ROM, FIU Wi-Fi, another FIU Wi-Fi. So those actually identifies individual access points that announcing on a specific frequency for a specific mode. Oh, not a specific mode, but rather range of the modes and kind of different maximum rates. This is basically it, what I wanted to define as part of our Wi-Fi discussion. Just remember that the structure of a Wi-Fi network is much more complex than in Ethernet. And even in Ethernet, we already have multiple types of different devices. In Wi-Fi, we actually not just different devices, but different types of communication. We can have a different type of structure that we can build using Wi-Fi. And remember, we have like stations, access point, basic service set, extended service set, the distribution kind of transport, and so on and so on. As I said, there is also much more complex structure of the link layer, and for the obvious thing that I already highlighted, there is actually more fields as part of the addresses. Like instead of 2 that we saw in Ethernet frame, there's like at least 4 and sometimes 6 in mesh case, for example. But in addition to addresses, we also have multiple types of frames. So instead of just having data frame, we have a control frame, we have a management frame, for the purpose that we need to announce something or join the network because you have to build this association. And besides that, we have multiple different standards that being defined. They define the physical layer, they define maybe a little bit the extension of the link layer, and Wi-Fi basically evolves over the years. Okay, so that's done for this part, and I will have one additional part that just a few more clarification about Wi-Fi, but I'll do it separately.